In early July 2025, something appeared at the edge of our solar system, not from another planet or the asteroid belt, but from a place beyond the pole of our sun, from the very fabric of space. This phenomenon was named Trian Atlas. When the James Webb Telescope turned its gaze on this cosmic visitor, its discovery shattered all our notions of comets that we thought were true. This is not a typical comet from our solar system. This is a messenger from another star system, possibly 8,000 years old, older than the Earth and our entire solar system. When the Webb infrared spectrograph captured the first light of Trian Atlas on August 6, 2025, the data received left astronomers in complete bewilderment. If you are interested in similar discoveries in the field of space, don't forget to subscribe. It's the best way to support our work. Also, let us know which city you are listening from. This scenario is based on facts and research using sources from the preprint repository archive, where Martin Coordinator from NASA's Goddard Space Flight Center published the results of the Webb Telescope observations on August 25, 2025. Data on observations was provided by the Near-Earth Object Coordination Center of the European Space Agency, published on September 19, 2025. These are not reports from major media, but scientific articles in which astronomers first expressed their astonishment at what Webb discovered. Let's return to the events that occurred on July 1st, 2025. In Rio Hurtado, Chile, the Atlas telescope, an asteroid impact warning system, detected something moving against the backdrop of stars. It was not unusual, as Atlas discovers cosmic stones every night. But this was different. Its trajectory described a hyperbola, not an ellipse, indicating it was not subject to the solar system's gravity. It was moving at a speed of 130,000 miles per hour. It was the fastest comet ever recorded. By July 2nd, 3 different observatories confirmed Atlas's suspicions. Telescopes in Canada, France, and Hawaii on Mauna Kea, the Lowell Observatory in Arizona, and the Deep Random Survey in Chile all recorded the same thing: a forming cometary envelope around the core. The Center of Small Planets announced its discovery. It was Trian Atlas, the third object confirming its status of cosmic interest. But then, the story becomes strange. Most comets begin to emit gases when they approach the Sun, at a distance of about 3 to 4 astronomical units. However, Trian Atlas began to form their cometary shell at a distance of more than 5 astronomical units, too early for a typical comet. On July 6th, 2025, the Hubble telescope captured its first images from a distance of 277 million miles from Earth. What the Hubble telescope discovered astonished astronomers. A cometary object shaped like a droplet was ejecting dust from its core. However, all size estimates turned out to be incorrect. The diameter of the core ranged from 440 meters to 5.5 kilometers, with the most likely size being less than 1 kilometer in diameter. For an object causing such activity at that distance, it must be much larger. And then came the call that all astronomers were waiting for: the launch of the James Webb Telescope, August 6, 2025. Target acquired. The NIRSPEC instrument is online. Spectral range from 0.6 to 5.3 kilometers. What Webb observed in these infrared wavelengths had never been seen in any comet before. The entire coma was saturated with carbon dioxide instead of water, which was unlike the typical mix astronomers expect. The pure and overwhelming outburst of carbon dioxide caused confusion. Webb's data showed the ratio of carbon dioxide to water, 8 to 1. This is the highest value ever recorded for a comet, 6 standard deviations above normal values for long-period comets. Statistically, this shouldn't exist. Nevertheless, it was shining an infrared light, and this could not be denied. Webb also discovered icy water, water vapor, carbon monoxide in normal proportions, and carbon disulfide, a compound with the smell of rotten eggs. The emission rates recorded by Webb tell a true story: 129 kilograms of carbon dioxide per second, 6.6 kilograms of water per second, 14 kilograms of carbon monoxide per second, and 0.4 kilograms of carbon disulfide per second. These are not evaluations but direct measurements using the most powerful infrared telescope ever built. The NASA SPRX Observatory confirmed Webb's discoveries from August 7th to 15th, 2025. Many telescopes conducted independent observations and obtained the same results. Comet 3 and Atlas differ from all previously known. Where did it come from? Analyzing its trajectory gives alarming answers. When astronomers track 3 and Atlas back along their trajectory, considering the gravitational disturbances from each star within 30 light years, they arrive at the core of the galaxy, the center of the Milky Way, located 30,000 light years away. If their calculations are correct, 3 and Atlas have traveled for 8 billion years. 8 billion. This makes it older than Earth. Older than our solar system by 3 billion years. This is the oldest object ever observed up close. Think about what that means. This comet formed when the Milky Way was young, before our solar system existed, when the materials that would later create Earth were still scattered in interstellar clouds. 3 and Atlas witnessed the birth of many stars. They experienced close encounters with remnants of celestial objects, accelerating through gravitational distortions around entities we cannot even imagine. And all this time, they preserved their pristine essence, encased in ice, waiting for the moment when they would enter our solar system and reveal their secrets to humanity. The prevalence of carbon dioxide is not a coincidence. Spectroscopic analysis shows 2 possible sources of its origin. Firstly, Tri and Atlas contain ice that has been subjected to radiation levels significantly exceeding anything ever experienced by comets in the solar system. Billions of years of cosmic rays and stellar radiation have slowly altered the chemical composition of the surface. Secondly, 3 and Atlas formed in the region where carbon dioxide condenses from gas to solid in its protoplanetary disk. This is the exact distance at which carbon dioxide transitions to solid phase around a young star, a region of formation that produces comets with a chemical composition exactly matching what has been recorded. However, there is a third possibility that worries astronomers. Low levels of water vapor may indicate something that hinders heat from penetrating deep into the core, some internal structure or composition that suppresses water sublimation, allowing carbon dioxide to freely escape. We have never seen anything like this before. We do not understand the mechanism, but we know that it is happening. If you are interested in such discoveries in space, support our work. Also, let us know where you are listening from. This research is based on data from preliminary archives where scientists publish their findings before peer review, providing us with the most current data. Now, let's return to the information. 3 and Atlas continue their journey to perihelion, their closest point to the Sun, which will occur on October 29, 2025, at a distance of 1.36 astronomical units, slightly closer than Mars's orbit. But this is not an ordinary flyby event for the comet. Mars will witness this phenomenon up close. Mars Express and ExoMars Trace gas orbiter of the European Space Agency will be ready to capture the trio and Atlas during its closest approach to Mars on October 3rd, at a distance of 30 million kilometers. Closer to Mars than ever to Earth. Martian orbiters will attempt to capture high-quality images using a high-resolution stereo camera and color stereo system. Many spacecraft and instruments are focused on an object that will not return here for billions of years, if it ever returns at all. The Coordination Center for Near-Earth Objects of the European Space Agency made precise trajectory calculations for the Webb and Atlas telescopes to observe a comet through its tiny field of view. This is an example of precise astronomy on an interstellar scale. Ground-based telescopes continue monitoring as the comet Atlas forms its tail structure. The Gemini South Telescope captured the growth of the tail on August 27, 2025. The team from the International Gemini Observatory, led by researcher Price Bowling from Eureka Scientific, recorded changes in particle composition as the comet heated up. The tail is not just dust. This is a chemical evolution occurring in real time as multi-billion-year-old ice finally meets sunlight. The Nordic Optical Telescope confirmed cometary activity on July 2nd, when David Jout and Jane Liu reported that the comet is moving towards the simplex plane. The team that discovered the first Kuiper Belt object confirmed that Comet Atlas is clearly active, exhibiting a diffuse coma structure. The 2-meter telescope of the Tidy Observatory also observed similar patterns of activity. Multiple independent confirmations, without errors, without illusions. Pure, observational science. However, the strangest discovery came from the TESS satellite, which was not searching for comets, but monitoring stars for exoplanet transits. Nevertheless, TESS captured the Atlas comet in its field of view and recorded something unprecedented. The comet had already begun to emit gases months before its discovery. TESS data for May shows clear cometary activity when Atlas was more than 5 astronomical units from the Sun, violating all known laws of comet activation distances. The very largest telescope detected gaseous compounds and atomic water vapor in the coma of Atlas in concentrations similar to those found in solar system comets. Familiar chemistry mingles with the alien. Mickey Transient Facility found images related to a previous discovery, dated May 21st, 2025. Multiple observatories independently documented an object that should not behave as it does, coming from a place it should not come from, displaying chemistry that should not exist. Tony Santana Ross published results in August 2025, showing that the Atlas comet is becoming redder throughout July as cometary activity increases. Color changes indicate the evolution of the surface composition, a material that has been frozen for 8 billion years and is finally sublimating. Ancient chemistry meets modern stellar radiation. The color change matches predictions for carbon-rich dust particles, exactly what to expect from a dominant carbon dioxide emission event. The numbers don't lie. Comet Tri and Atlas have diameters ranging from 5.6 kilometers to possibly 440 meters. The uncertainty in size is due to its unusual reflective ability. Most comets reflect about 4% of sunlight, but Tri and Atlas reflect enough light to confuse calculations. Its surface is brighter than expected, possibly due to the impact of cosmic rays over billions of years, leading to the formation of unusual crystalline ice structures, and perhaps due to the presence of materials previously unknown to scientists. The speed of the comet tells its own story: 130,000 miles per hour relative to the Sun. Extraordinary speed and a parabolic trajectory indicate acceleration that occurred billions of years through gravitational interactions with stellar objects. When Tri and Atlas leave our solar system, it will move even faster. The gravity of our Sun will give it additional momentum, sending it deeper into interstellar space at speeds that will allow it to reach other star systems in a brief cosmic moment. Observations of the comet are scheduled for December 2025, when it will reappear after solar conjunction. At that moment, the comet will begin to actively vaporize gases. Passing through perihelion will change everything: surface chemistry, internal heat distribution, sublimation patterns. December observations may reveal entirely new spectral features, as centuries-old ice reaches temperatures not experienced since the formation of Tri and Atlas around its parent star. The Hubble telescope will continue monitoring until November, using ultraviolet spectroscopy to determine the ratio of sulfur to oxygen in gas emissions. The observations will reveal atomic transitions invisible to other wavelengths. This provides information about elements that describe the formation process, the signs of nucleosynthesis of the star system where Tri and Atlas formed, and the chemical lessons of the entire galaxy. These conclusions may have important implications for astronomy. If Tri and Atlas represent typical chemistry of interstellar comets, then our models of planetary system formation need to be revised. If carbon dioxide-rich comets are common around other stars, it means we have been studying an unrepresentative sample for decades. Each comet in our solar system formed under the same stellar conditions, while Tri and Atlas formed around another star in different radiation conditions in a stellar environment that existed 8 billion years ago. This is a comparison of planetary science on an interstellar level. Data about Tri and Atlas provide us with the first detailed chemical analysis of material from another planetary system. The ratio of carbon dioxide to water indicates different formation conditions, unlike anything in our solar nebula. Perhaps higher levels of radiation were destroying the ice of water, or formation was occurring in areas with specific temperatures where carbon dioxide dominated the chemistry of ice. Age estimates create their own problems. If the comet Tri and Atlas is truly 8 billion years old, then it predates most star formation in the Milky Way. It formed when the galaxy was younger, poorer in metals, and inhabited by various stellar populations. Her parent system could contain elements in proportions completely different from the solar composition. We are exploring not just an alien comet, but chemical traces from an earlier stage of galactic evolution. Comet Tri and Atlas will pass closest to Earth at a distance of 1.8 astronomical units on January 15th, 2026. This distance is still too great for detailed observation of the surface, but close enough for continuous spectroscopic monitoring during peak comet activity. Then she will disappear forever, returning to interstellar space, wandering between the stars for billions of years until chance brings her to another planetary system. Unless we intercept her first, there are proposals for rapid flyby missions, spacecraft designed for launch with minimal delay upon detection of interstellar objects. Their speeds will surpass all previously achieved. These are engineering challenges that will elevate propulsion technologies to their limits. But the scientific results could revolutionize our understanding of other star systems, providing the opportunity for direct sampling of materials from alien planetary systems and analysis of chemistry impossible for ground-based telescopes. Time is running out. With each passing day, the comet Triton Atlas penetrates deeper into the inner solar system, heating up, losing mass, and changing composition. The ancient chemistry of 8 billion years begins to sublimate. By the time it reaches perihelion, ancient traces will vanish, giving way to subsurface materials that may tell a completely different story. We observe as the chemical traces of another era in the galaxy evaporate before our eyes. The detection capabilities of the Webb Observatory significantly surpass the observational abilities regarding the comet Triton Atlas. The telescope can detect similar objects at distances where ground studies cannot capture them. Weaker comets, more distant approaches, objects passing through the outer solar system without forming visible tails. The era of routine detection of interstellar visitors has begun. Comet Triton Atlas will not be the last, and perhaps not even the most unusual. Statistical models suggest that interstellar objects are the most common large bodies in the Milky Way. There are many comets and asteroids that were ejected from their planetary systems during their formation and now wander between the stars. Periodically, they pass through our solar system, giving us the opportunity to study them. Chris Lintott from Oxford University believes that at any given moment, there is at least one interstellar guest within our solar system. However, we have not yet developed the technology for its systematic search. The Rubin Observatory will change this situation. With the start of scientific operations in 2025, Rubin will explore the entire visible sky every 3 nights using automated algorithms to detect moving objects. Interstellar visitors will be identified within hours of entering the observation area. We can expect several objects per year, which will provide us with enough data for statistical analysis of interstellar comet populations, as well as tracking them back to their source systems and determining galactic distribution patterns. However, Comet 13 Atlas remains unique. Its chemical composition, containing carbon dioxide, its age, and probable origin from the core of the galaxy, create ideal conditions for study using humanity's most powerful telescopes. This occurs at the moment when we are developing technologies to unravel its mysteries. A journey spanning billions of years through interstellar space. 8 billion years of cosmic evolution led us to August 6, 2025, when the instruments of the Webb Observatory focused on this object and captured the infrared light of the oldest object ever studied by humanity. Data continues to come in. Observations from the near-spec Webb Observatory contain spectral lines that have not yet been fully analyzed. Isotope ratios may reveal patterns of stellar nuclear synthesis from the original system. The proportions of carbon-13 to carbon-12 are partially obscured by dust but will be revealed in the future analysis process. Molecules of heavy water have been discovered, as well as molecular species that exist only under specific radiation conditions. Chemistry textbooks are written in the light of an object older than Earth. Atlas carries not only ancient ice, but also information about the formation of star systems 8 billion years ago, radiation conditions in various galactic regions, the chemistry of planetary systems under conditions that no longer exist, and cosmic evolution on scales we have never directly observed. We are studying not just a comet, but deep time, geological timescales recorded in cosmic ice, archaeology on a galactic level. The trajectory analysis shows the future of Atlas 13 as clearly as its past. After passing perihelion, it will make a turn around the Sun and return to interstellar space, moving at a speed of about 40 kilometers per second relative to the solar system, heading towards the constellation of Insa, its destination. Other star systems, other planetary neighbors. New opportunities for exploration for alien astronomers who may wonder where this ancient wanderer originated. In 40,000 years, the 13th Atlas will pass within less than 2 light-years of the star Wolf 359. This red dwarf star is surrounded by unknown planets. If Wolf 359 contains technological civilizations, they will be able to detect the approaching 13th Atlas towards their system, just as we detect its movement towards ours. They will direct their powerful telescopes at the visitor. They will analyze its spectral signatures. They will find traces of carbon dioxide and ponder its origin. Perhaps they will trace its trajectory back through space and realize that the 13th Atlas came from the direction of our solar system. They will wonder if there was life on the third planet from the yellow star when the 13th Atlas passed by. They might find isotopic signatures in its ice that match data about the composition of the stars in our galactic neighbor. Archaeology of interstellar space. Messages written in the chemistry of comets, transmitting information across cosmic distances through the patient migration of prepared messengers. But above all, the 13th Atlas must survive its encounter with our Sun. Passing through perihelion subjects comets to extreme thermal stress. Surface temperatures reach hundreds of degrees. Internal pressure from rapid sublimation can cause structural damage, fragmentation, and complete destruction. Many comets do not survive their first close approach to the Sun. The 13th Atlas traveled 8 billion years to reach this moment. Its survival depends on an internal structure that we cannot observe directly. Observations from the James Webb Telescope in December will answer this question. If the 13th Atlas successfully emerges from perihelion, it will provide unprecedented data on the composition of 8 billion-year-old ice under extreme heating conditions. If it breaks apart, the cloud of debris will reveal the internal structure and allow for the analysis of subsurface material that has never been exposed to the space environment. Either outcome will advance our understanding of the composition and evolution of interstellar objects. Scientific articles continue to emerge in the archive. Martin Coordinate's team from NASA Goddard has published initial results of spectroscopy using the James Webb. Colin Wilson from the Near-Earth Object Coordination Center contributed to trajectory analysis for Mars orbital observations. David Jeve from the University of California, Los Angeles led the Hubble Telescope imaging campaign. Price balling from Eureka Scientific coordinated observations with ground telescopes. Unprecedented international collaboration. Each major observatory provided its data. Every available equipment was focused on the same task. Such is the essence of science when it comes to something truly unprecedented. No gradual testing of hypotheses, no slow progress. This revolutionary discovery demands immediate attention from the entire astronomical community. The TRES and ATLAS projects compelled astronomers to mobilize resources, coordinate observations, and exchange data in real time. The timeline of discovery is measured in days and weeks, rather than the usual years and decades of meticulous research. Spectroscopic analysis methods have pushed the telescope's capabilities to the limit. Observations and spectral errors were at the edge of sensitivity. Signal processing extracted molecular signatures from noise levels that could overwhelm less advanced instruments. Calibration procedures were specifically designed for fast-moving objects with unusual spectra. These technical advancements pushed infrared astronomy beyond the applications of the TRES and ATLAS projects. However, a deep mystery remains unresolved. Why carbon dioxide? Why such extreme proportions? Why does the chemistry of formation differ from everything in our solar system? Answers require understanding the stellar conditions 8 billion years ago, the chemical evolution of the galaxy, fields of interstellar radiation, the formation of planetary systems in conditions that we can model but can never observe directly. The TRES and ATLAS projects may represent normal chemistry of interstellar comets. The comets of our solar system may be an exception, formed in an unusual stellar environment that led to water-rich ice chemistry. We explore the exception, believing it to represent the rule. The TRES and ATLAS projects suggest that we were wrong in our fundamental assumptions about comet formation in the galaxy. Either TRES and ATLAS are truly unique, objects with billions of years of formation history, different from typical interstellar comets. Random encounters with radiation could alter its surface chemistry. A collision with another interstellar object might mix its compositions. Internal heating from radioactive decay could cause unusual sublimation patterns. The sample size of detailed observations of interstellar comets still stands at exactly 1. Scientific articles acknowledge these uncertainties, cautiously commenting on preliminary results, calling for additional observations, and recognizing that studies of individual objects cannot support broad conclusions about populations of interstellar comets. However, the data remains independent of interpretation. The ratios of carbon dioxide to water are 8:1. Production volumes are measured in hundreds of kilograms per second. Spectral signatures distinct from any objects in the solar system. Repeated observations in December will confirm or change these conclusions. Extended spectral coverage, different conditions of solar heating, possible detection of additional molecular species as deeper layers of ice sublimate. Data from December may help clarify questions about partially hidden isotopic ratios found in August, including carbon isotopic signatures of the parent star and oxygen isotopic patterns demonstrating formation temperature conditions. Meanwhile, 3 objects continue their hyperbolic journey to perihelion. They heat up, accelerate, and develop a visible tail in ground-based telescopes. Chemical evolution occurs in real time as ice aged 8 billion years first encounters sunlight since its formation. We witness fossil chemistry from another era of galactic evolution being revived under the influence of our sun. Observations of Mars in October will provide various perspectives. Numerous spacecraft with different instruments. Observations impossible from Earth, as Mars will be on the opposite side from 3 objects during its closest approach. Stereo images that can clarify the core's rotation and surface characteristics. Composition gradients in the coma, indicating variations in sublimated chemistry. The Mars Reconnaissance Orbiter joins the observational campaign with its high-rise camera, designed for surface imaging, but also capable of astronomical observations. The Curiosity and Perseverance robots will try to capture if 3 objects become bright enough for observations from the surface. Numerous NASA missions are coordinated for a single goal: unprecedented multi-platform astronomy focused on one interstellar object. The coordination tasks are immense. Spacecraft designed for various missions, equipped with tools optimized for planetary observations rather than astronomical ones. Temporal requirements demanding precise positioning in orbit. Delays in communication between Mars and Earth complicate real-time observation coordination. Engineering issues are being addressed specifically for the observation of 3 objects. However, the scientific justification for these activities is overwhelming. This is the closest approach of any interstellar object to Mars in recorded history. The next similar opportunity may not happen for thousands of years. The geometry of observing Mars provides impossible angles of view from ground telescopes, allowing the study of the 3-dimensional structure of the coma, measuring the core's rotation, and revealing surface features at the edge of resolution. The challenges of data integration are equally complex. Different tools, various calibration standards, different data formats, and analysis software. The obtained results must be combined to create comprehensive models of the composition and behavior of 3 hiatuses, as well as to establish international agreements on data exchange, standardized processing procedures, and quality control for unprecedented monitoring methods. Nevertheless, the results justify all efforts. We study 8 billion years of cosmic evolution preserved in ice, the chemistry of an earlier stage of galactic development, the conditions of formation around stars that died before the emergence of our solar system. The transmission of information through space and time is achieved through the patient migration of frozen files. 3 hiatuses represent the oldest known objects in our cosmic neighborhood: older than meteorites, older than the oldest terrestrial rocks, older than the oldest lunar samples. 8 billion years of continuous existence in the deep freeze of interstellar space without atmospheric influence, geological processes, or biological contamination. The pure preservation of ancient chemistry awaits 8 billion years to be discovered by human science. The consequences of this discovery go beyond astronomy. Astrobiology considers 3 hiatuses as potential carriers of organic compounds from other star systems. Panspermia hypotheses suggest that interstellar objects can carry life between planetary systems, serving as chemical precursors to biological processes. Organic molecules that survive interstellar radiation. Seeds of life, scattered across the galaxy by wandering comets, search for organic signatures in the coma of 3 hiatuses using spectral analysis. Carbon compounds beyond simple carbon dioxide and carbon monoxide. Methane, formaldehyde, hydrogen cyanide. These are precursors to amino acids, molecular species that bridge the gap between simple chemistry and biological complexity. The limits of sensitivity bring detection capabilities to theoretical boundaries, but the detection of organic compounds faces contamination issues. Comets in the solar system contain organic molecules formed in our stellar nebula. Distinguishing local organic chemistry from extraterrestrial requires isotopic analysis, which exceeds current capabilities. Ratios of carbon, 13. Nitrogen signatures, 15. The abundance of oxygen, 18. Isotopic patterns indicating stellar nucleosynthesis of the parent system. The search for biosignatures remains speculative. No confirmed discoveries of biological compounds have been recorded in any interstellar object. Protocols have not been developed to distinguish between organic biochemistry and biotic chemistry in comet spectra. There is no consensus on what can be considered convincing evidence of life transfer between star systems. Nevertheless, the search continues, as its results could revolutionize our understanding of the cosmic distribution of life. Objects known as Tri and Atlas are also significant for planetary defense. Interstellar objects approach from random directions at high speeds. Current detection systems assume that objects originate from the solar system and follow predictable orbits. Interstellar visitors appear unexpectedly with minimal warning time. The likelihood of a collision remains low, but the consequences could be catastrophic. The Atlas surveillance system, originally designed to detect asteroids in the solar system, accidentally discovered interstellar objects. Target systems for detecting interstellar visitors will require different monitoring strategies covering the entire sky, using highly sensitive instruments and automated analytical systems capable of distinguishing interstellar trajectories from solar system trajectories within hours of detection. However, TRI and ATLAS do not pose a threat to Earth, as their closest distance is 1.8 astronomical units. The probability of impact is absent, there are no gravitational disturbances in Earth's orbit, and there is no danger from tail debris, providing a clean scientific opportunity without complications related to risk assessment. This is the perfect interstellar visitor for detailed study without the complexities of risk assessment. The observation window continues to narrow. Each day, TRI and ATLAS approach solar conjunction, after which they become invisible from Earth. The period from November to December, when they disappear behind the Sun as seen from our planet. Observations from Mars partially fill this gap, but inevitably there are large data gaps. The critical passage through perihelion occurs during conjunction when ground telescopes cannot observe, while space telescopes continue monitoring, including Webb, Hubble, solar, and heliospheric observatories, and spacecraft positioned at various angles around the Sun. Partial coverage during the most important phase of TRI and ATLAS passing through the solar system, a period when 8,000-year-old ice collides with maximum heating, revealing its deepest chemical secrets. The return in December will show whether the TRI and the ATLAS have survived entirely after passing perihelion. Fragmented objects display various spectral signatures, forming debris clouds with separate components and chemical segregation, where different types of ice sublimate at varying rates. The internal structures that were inaccessible during the approach are now becoming apparent. The surviving objects show altered chemistry, layers of surface that have peeled away, and an exposed substrate containing different isotopic ratios of material that has not been affected by cosmic weather for 8 billion years. Fresh surfaces reveal the chemistry of formation, untouched by cosmic rays, as well as archaeological layers in cosmic ice, capturing various epochs of cosmic evolution. Observations will continue until spring 2016. Ultraviolet spectroscopy of the Hubble telescope and the extended infrared coverage of the James Webb Telescope. Washington, Padua, Ninen, Dios. Ground telescopes track 3 asteroids as they move away from the inner solar system. The signals gradually fade, spectral lines weaken, a slow farewell to humanity's oldest visitor. By the summer of 2016, 3 instruments will become too weak for detailed spectroscopic observations. The window for data collection will close forever. The analysis will continue for many years using archival observations, but there will be no new data, and no further opportunities are anticipated. There is nowhere to return. A journey of 8 billion years through space will conclude in just a few months of human observations before it fades back into the darkness of interstellar space. The inherited data archive will support decades of research, spectral libraries, composition models, theory verification, comparative planetology studies, using a single detailed chemical analysis of material from another star system, doctoral dissertations, postdoctoral research projects, theoretical articles exploring the implications for the chemical evolution of the galaxy. However, direct science will focus on extracting maximum information from existing observations, analyzing isotopic ratios that push the limits of the James Webb Telescope's sensitivity, identifying molecular species in spectra, calculating production rates based on multi-period observations, and constraining core sizes based on photometry and thermal modeling. Every available analytical technique will be applied to the oldest object ever studied by humans. International cooperation in research continues to expand. European Astronomical Observatory, Japanese Space Agency, Indian Astronomical Institutes, Chinese Academy of Sciences. Global coordination for data exchange and analysis. This will be the first truly international study of an interstellar object. Scientific diplomacy through joint research of cosmic visitors. Project 3 and ATLAS has transformed the science of interstellar objects, moving from speculation to observational astronomy. Detailed data on the chemical composition, precise measurements of trajectories, and multispectral observations across the entire electromagnetic spectrum were obtained. This became the foundation for statistical studies when future interstellar visitors are detected. Observations serve as a template for comparative analysis. The next interstellar visitor may appear next year or in a decade. This random timing, based on galactic dynamics, goes beyond human prediction.